Section 2.3 is called valid and invalid arguments. Argument in math is simply it's a sequence of statements ending in a conclusion. So in this section, we're not going to show if something is an argument or not, but our goal is how to determine if an argument is valid or invalid. So here's an example of an argument. If Jenny doesn't eat her dinner, she will be hungry. Jenny isn't hungry, therefore Jenny ate her dinner. So later on, we're gonna prove if this is a valid argument or not a valid argument. And then if we just change these sentences to PQ form, so if Jenny doesn't eat her dinner, so this is the P, then Q. So if P, then Q. This premises is not Q, so Jenny is not hungry, so it's not Q. Therefore, Jenny ate her dinner. It's the opposite of the first premises, which is Jenny ate her dinner. So in order to decide if an argument is valid or not, we're going to have to follow these three steps. First step is we're going to identify the premises and conclusions of the argument form, and then we will construct a truth table. And the truth table is going to show the truth values of all of the premises and the conclusion. And then we're going to only be interested in the rows, which are called critical rows. And a critical row means a row of the truth table in which all the premises are true is called a critical row. So we're going to look at the premises situation. If both of the premises are true, these are called the critical row. And if there's a critical row in which the conclusion is false, then it is possible for an argument of the given form to have the true premises and a false conclusion. So the argument will be invalid. If the conclusion in every critical row is true, then the argument form is going to be a valid form. So we're going to look at an example to follow these steps. So the example is we want to prove that the following argument form is valid. So let's look at that argument form. P, if P then R, if Q then R, therefore, if P or Q then R. So this is the first premises, if P then R. This is the second premises, if Q then R. And this is the conclusion here. So we have two premises, and then this is the conclusion here. So we have PQR, so half of the P is true, half of the P is false. Then every two of the rows will be switching between true and false for Q, and then R will switch between true and false. So we got all the combinations of PQR. First, we're going to look at if P, then R. Remember, we learned this in the very first lesson, that this statement's truth table only becomes false one time whenever the first one is true, but the second one is false. So for P and R, so whenever the first one is true, but the R is false, those are the only time we're going to get false. Everything else case is going to give us a true statement. So this is for if P, then R. Now we're going to look at the second premises, which is if Q, then R. So this is my Q, and this is my R. For everything else, we will have true, true, except if the first one is true, but the second one is false, we will have a false result like this case. If the first one is true, but the second one is false, we will get a, for if Q, then R, we will get a false result. So this will be the truth table for if Q, then R. Now we have another, now we're going to jump to the conclusion. The conclusion is if P or Q, then R. So first we need to find the P or Q true statement. So for P and P or Q, we only get false, false for the last two lines. So this is the truth table for P or Q. Now we're going to compare this with R. And because that's if P, if and else, if P or Q, then R case, this only becomes false if the first one is true, but the second one is false. If the first one is true, but the second one is false. If the first one is true, but the second one is false. So if we look at this truth table here, we got false here, we got false here, and we got false here. Now, remember, step one is we did identify the premises and conclusions of the argument form. So premises one, premises two, conclusion. Then we did construct the truth table showing the truth values of all the premises and the conclusion. Now we're going to find the critical rows. For critical rows means both of the premises must be true. So since we have two premises here, and these are the dark gray lines are the lines that we need to look that both of the premises are true. And now we're gonna almost ready to decide because we are able to locate the critical rows. Now, if both of the premises are true, but the conclusion is false, we're gonna call it invalid. So look, these two are true, the conclusion is true, so this is a good thing, right? Both of these are true. The conclusion is true. Both of these are true. The conclusion is true. So here we have highlighted first, third, fifth, seventh, and eighth rows as critical rows because again, critical rows means both of the premises must be true. In critical rows, we're going to check the value of the conclusion and we are going to notice that it is true in each critical row. So in each critical row, we got these truth case. Therefore, this is going to be a valid argument for this case. Now let's take a look at another example here. And we're going to determine if the following argument is valid. So the first one is Jenny drinks either tea or coffee in the morning. Jenny drank tea this morning. Therefore, Jenny did not drink coffee. So for this, let's form our argument first. So P means drinking tea, Q means drinking coffee. So for this one, we want tea or coffee. So the first premises will be P or Q. Then Jenny drank tea this morning. So we got the tea, which is P. Therefore, Jenny did not drink coffee, so we have not Q. So we have the truth table here for P, Q. So we need to, this is our first premises, which is P or Q. And then we already have the P, and then the conclusion is not Q. So it is the true, true, false, false, and Q is alternating between true and false to get all the combinations of true and falses for P and Q. So first, we're going to find the truth table for the first premises, which is P or Q. So or is only false when both of them are false. So this is the truth table for the first premises. And this is the truth table for the second premises, right? Now, we're going to also need the conclusion, and conclusion is not Q. So this true will be switched to false, false will switch to true, true will switch to false, and false will switch to true. Now, this is a premises, and this is a premises. So let's find the critical rows. Critical rows are just first, and the second one is the critical row. But when we look at these two critical rows, not always we get the true for the conclusion. So this becomes an invalid argument because of the first line that is false as a conclusion. It is important to understand what it means for an argument form to be invalid. It doesn't mean that the conclusion is always false. It means that not all of the conclusions are true when the premises are true. So there are some very common argument forms that we will refer to often by name. We won't prove that these are valid here, but two of the most common ones are magis ponens and magis tollens. So these are very famous. So I wanted to just mention them here. Magis ponens, it means the way of affirming. So if you look at what magis ponens are, if P, then Q, P, therefore Q. If you look at this meaning, the form will be always if P then Q, and then P is true, therefore Q is true. So if we explain this with some real life sentences, so the first premise is if it rains, the ground gets wet. It rains, so the ground gets wet. So this is an example of Marge's ponens, which is a way of affirming. Now we're going to look at Marge's tolerance, and Marge's tolerance means the way of denying. And it will always the form of if P then Q, not Q, therefore not P. Again, if we look at the same example, so if it rains, the ground gets wet. So they start with the same premises here. Now we're gonna deny the Q, so we're gonna say the ground is not wet, so it did not rain. So the key difference is Marge's ponens start by saying the first part is true. Marge's tolerance start by saying that the second part is false. So also here, there's something that I want to mention. It's called hypothetical syllogism. So it's also very famous argument. If P then Q, if Q then R, therefore if P then R. This is called hypothetical syllogism. So the key difference is Marge's ponens start by saying the first part is true. Again, Marge's tolerance starts by the second part to be false. Okay, so here I want to also talk something else, that we need to make a distinction between validity and truth. We're focusing on validity right now. So let's take a look at valid argument that has a false premise and false conclusion. So if Euclid studied geometry, then Euclid had blue hair. Euclid studied geometry, therefore Euclid had blue hair. So this argument is valid. You can also create a truth table if you want to, because its form is Marge's ponens. So remember the Marge's ponens form. If P, then Q, P is true, therefore Q is true. But the first premise, sometimes called a measure premise, which is this one, is false, and so is the conclusion is false. So this one is false, so the conclusion is false. So Euclid didn't have blue hair, because this one is not a true statement, but it is still a valid statement, valid argument. A fallacy is an error in reasoning that gives us an invalid argument. The book discusses a few different kinds of fallacies, but here we want to give two specific argument forms that are invalid. One of them is a converse error, the other one is an inverse error. Converse error is if P, then Q, Q, therefore P. So this is called converse error. For inverse error, if P, then Q, not P, therefore not Q. Also, these two are called a fallacy. It's an error in reasoning, which is going to give us an invalid argument. So now let's say an invalid argument with true premises and a true conclusion. If Harry Truman is president of the United States, then Harry Truman must be 35 years of age or older. Harry Truman is 35 years of age or older. Therefore, Harry Truman is President of the United States. So this is an invalid argument with true premises and true conclusion. Now, the first premises is if Harry Truman is President of the United States, then he must be 35 years of age or older. So this is true. And then Harry Truman is 35 years old, age or older. This is also true. Therefore, he is the President of the United States. At least during his presidency, both premises and the conclusion were true, but this is an invalid argument because it makes the converse error. So if you look at the converse error, then we have if P then Q. So if P then Q, we've got the Q, therefore P. When you repeat this, this is called the converse error. The distinction we will make in order to arrive at truth is the distinction between an argument being valid and sound. So an argument is called sound if it is valid and its all premises are true. An argument that is not sound is called unsound. We're going to look at the contradictions in valid arguments. The concept of logical contradiction can be used to make inferences through a technique of reasoning called the contradiction rule. Contradiction rule, if you can show the supposition that statement not P leads logically to a contradiction, then you can conclude that P is true. So let's look at this one. So we have the contradiction rule. We want to show that following argument form is valid, where C is a contradiction. So the argument is if not P, then C, therefore P. So we need P, not P, we need C contradiction, and then we need the if not P, then C truth table, and we need the conclusion. So for P, it will switch between true and false. So not P will be false and true. C, contradiction means just false and false all the time. So if P, then C will be only false if the first one is true, but the second one is false, which is the second one. So this is the only one that it is true here. Now the conclusion is just a P. The conclusion is here P, which is true. So the both premises, this one, we can also prove this contradiction rule by some using algebra. So remember the first premises is if not P, then C. If not P, then C. We learned this last class that we can just rewrite this as not P or the second one. We can rewrite it like this. So two negatives, they will create a positive. So this will be just P or, and contradiction is always a false statement. So whenever you or your P with a false statement, the result depends on your P. So this is how we can prove this contradiction rule. And remember, in this case, when the premises is true and the conclusion is true, this is how we get the true, only it becomes when the P is true. So when we look at this table, I have a summary of the valid argument forms. The first one is the Magis ponens, which is the if P then Q, P then Q, and Magis tollens is if P then Q, not Q, then not P. And then we have this called generalization, we have the specialization, conjunction, elimination, and transitivity here. As a reference, we can look at these tables. In summary, for an argument to be valid means that every argument of the same form whose premises are all true has a true conclusion, and an argument to be invalid means that there's an argument of the same form whose premises are all true and whose conclusion is false. For an argument to be sound means that it is valid and its premises are all true. In this case, we can be sure that its conclusion is true.